Okay, hello everybody once again. We're going to move on through chapter 2.4, in particular continuing our discussion of different ways that we can measure variation in a set of data, and with a big focus on standard deviation here. Standard deviation measuring basically how much a set of data tends to be away from the mean. And last time we talked about just what standard deviation really was, how higher standard deviations indicate data that tends to be further away from its center as opposed to lower standard deviations. And now we want to focus on this guy down here, number 2. We want to talk about that formula for standard deviation that I gave you just a peek at last time, and what it is and how we can actually go about explicitly calculating standard deviation given a set of data. And so these were the two formulas that you saw last time. On the left down here, I have the standard deviation for a population. This is the real formula down here. And on the right, I have the standard deviation for a sample. And notice that once again, we're following this convention where when we're using a sample, we're using Latin letters like A, B, C, D. So we have X bar for the mean, and we'll use S to denote the standard deviation when we're dealing with a sample. If we're dealing with a population, we'll adopt slightly different notation. The mean, you should still remember, is this Greek letter mu, mu for the mean. And our standard deviation will be denoted by the Greek letter for S, which is sigma. That's lowercase sigma here, is this letter right here. Of course, capital sigma is what we use for summation. So those are our two formulas for standard deviation. But where do they come from, and how does this represent anything like distance from the mean? Well, if you remember last time with our Scotiabank example, we ended up actually calculating the average distance from the mean. And the way that we did that, what did we do? How did we find average distance from the mean? We took every point x and we subtracted the mean, x bar, or mu if we were dealing with a population rather than a sample. So we took x minus the mean. When somebody had been in line for 4 minutes and the mean was 6 minutes, we took 2. If they'd been in line for 11 minutes and the mean was 6 minutes, we would have taken 5. So we didn't just take x minus x bar, we actually took the absolute value when we found average distance from the mean. Then we added up all of those values, x minus x bar, and we divided by the sample size. In our case, it was always 3. And this is how we found our average distance from the mean. So does that formula that I just drew really look all that different from standard deviation? Well, it's a little bit different, and we'll explain exactly where that difference is. The sum of x minus x bar over n, or the sum of x minus mu squared over n, square rooted. So where does all this stuff come from? Well, we can go ahead and reconstruct our formula basically from the inside out. So just like at the bank, the first thing that I want to do when I want to measure something like typical distance from the mean is I want to take each of my data points x, and I want to find out how far they are away from the mean. So I take x minus mu, or I can take mu minus x if my point happens to be lower than the mean. And in either case, if I'm trying to measure distance, I want my distance to be positive. So in our absolute value example, where we did x minus x bar, or x minus mu, this is how I found average distance from the mean, keeping my values positive. In the standard deviation case, we need the same thing. We never want to have a negative distance, so we adopt a slightly different convention, and that is to square our value rather than take absolute value. You might think absolute value is easier and is a better choice for measuring distance, but as it happens, absolute value brackets are kind of difficult to deal with in a lot of mathematical formulas, and the standard deviation formula doesn't deal with them. It squares things to turn them positive instead. It ends up being more beneficial in the long run of statistics. So we first find our value x minus mu. That's called the deviation of the particular data point, x. And then to find its distance from the mean and ensure that it's positive, we square it. We get x minus mu squared. And if I do this for one data point, then I do it for all of the data points. And I get a big long list of everybody's distance from the mean squared. So I take all of the points of my data, they're all a different distance from the mean, I square all those numbers, and then what do I do with them? Well, just like before, I don't want to just keep them as is. I take their average. To get a sense of average distance from the mean, I added up my values and divided by n. What I want to do now is I want to find the average of all of these deviations squared. So I take all of the x minus mu's, I square them, I sum them all up, and I divide by however many points I had. And in the assumption that it's the population, I use capital N to denote my sample size. And this value here, the sum of x minus mu squared over n, is called the variance of the population. What it is the average squared distance from the mean. It's not the average distance from the mean. If I was in the case of Scotiabank, my units here wouldn't be minutes. It would be something like minutes squared, which I don't really have a good interpretation for. It would be minutes squared, right? I would be saying things like, you know, this person was, instead of 5 minutes, I'd have something like 25 minutes squared. And that's not a very good thing, right? I don't want to leave an interpretation out of the units that I started in. So this value, the variance, which is the sum of x minus mu squared all over n, in order to bring it back into that, the right scale and the right units in particular, what I do is I just go ahead and take the square root of it. And this is what standard deviation is. And that's where the formula comes from. Again, it looks very similar to our average distance from the mean. I keep doing x bar, I'll switch it to mu over n. There's not a big difference here. The only difference is that in this case, I squared it and then took the square root. And of course, I dropped the absolute value brackets because I don't need them if I'm going to do my squaring trick to make everything positive. So that's how standard deviation and average distance from the mean are similar, and both in effect measure the same thing, albeit with very slightly different ways. The only difference being squaring instead of absolute value brackets. And so that's the formula, but let's go ahead and, you know, this is the kind of thing that you need to practice a little bit before you go ahead and understand it, especially how to use it. So let's go through the steps of actually calculating a standard deviation. So on the left over here I have a list of BMI scores, that's body mass index, for a group of men or women or whatever it is. And I want to find the standard deviation of this set. So if I mean to measure the average distance from the mean of a set of data, or the standard deviation, of course the first thing to do is to make sure that I actually know what that mean is. So the first thing I do with any set of data if I want standard deviation, step one is I find the mean. And what's the mean of this data on the left? You guys know how to do that. I just take all these points, I add them up, I divide by however many I have, which in this case it looks like it's 12, and I get 25.3 is the average of these numbers here. Okay, so you can double check yourself to make sure you know how to do it, but in this case it's 25.3. After I find the mean, I need to find out how far away each point is from the mean. So my next step in this formula is to go ahead and calculate the value of x minus the mean. So my mean was 25.3, and so what I have to do is I have to take each of these values and subtract the mean. 23.8 minus 25.3 gives me minus 1.5. This value is 1.5 units away from him. He's 1.5 away from the mean. Similarly, this guy is 2.1 units away from the mean. So I write minus 2.1. As it happens, this negative sign isn't actually even really important because the next step to do is to square this, so the negative sign goes away anyways. But for now, we can write the negative sign if we want. If I look down the road at all of these numbers, how far away is 24.5 from the mean? That's 0.8. My further points away from the mean are the points with the higher deviation. 31.4, for instance, is 5.9 units away, and so on and so on. So step two, to find my standard deviation, is I find the deviation after I find the mean, and I do that by subtracting every point from the mean. Okay, so what's the next step? I have all my deviations. Well, the next step is to square them. I have all these negative numbers in here, and those are ugly, and they don't represent the distance that I want. So to turn them positive, I square them. It gets rid of all my negative signs. This is just an easy step. I just find x minus mu squared. So minus 1.5 squared, 2.25. Minus 3.8 squared, 14.44, and so on and so on. All I do is take each value here and square it. And of course, I should never have any negative numbers left after I do my squaring. Now that I've got all my squared deviations, the fourth step is just to take their average. So I'm finding the average squared distance from the mean. So I take all of these numbers just like before. It's my sort of second average calculation of the day. I found the average of the BMI scores first. Now I need to find the average of these numbers here. There's 12 numbers, and I just find the average in the usual way, 2.25 plus 4.41, and so on and so on and so on. I add them all up right down to the very end. I divide them by the number of data points there are. In this case, there seems to be 12. And you can go ahead and double check this calculation for me too, but it looks like I get 83.15 over 12, which gives me about 6.9. So my average squared distance from the mean is 6.9. And this is, again, it has a special name that you might see pop up once or twice. It's called the variance of my data. And so do you remember the last step? What is that final step? The final step to finding standard deviation is we take this number that we got and we just quite simply take its root. This represents 6.9 squared units away from my deviation, but I don't want to talk about squared BMI scores. That doesn't make any sense to me. I want to talk about how many BMI points do I tend to be away from the mean. So I take the square root of this and it brings me back to that original data unit. So I have square root 6.9 is approximately 2.6, and so I conclude by saying the standard deviation of these BMI scores is 2.6. So my mean was 25.5, was it? I already forget the mean. 25.3, and the standard deviation of 2.6 tells me that the average BMI score is 25.3, and people tended to be about 2.6 units away from that on average. That's how I can interpret that. I can draw further conclusions about it based on what we do know about standard deviation, and that's what we talk about next. How can I be a little bit more concrete about this? How can I add things like saying which percent of my population can I expect to be within a certain range of the standard of the mean, and so on and so on. But for now, we're just worried about finding standard deviation, and in this particular case, the answer to this problem is the standard deviation is 2.6 BMI points.